On your desk computer, for every kilogram of matter we can see, from distant stars and galaxies, there are 5 kilograms of invisible matter surrounding us. This dark matter is a mysterious entity that eludes all forms of direct observation, yet its existence is felt through the invisible gravitational pull it exerts on visible objects. 50 years ago, physicist Stephen Hawking proposed an idea about what dark matter could be, a population of black holes that might have formed right after the Big Bang. These primordial black holes would not be the giants we detect today but microscopic regions of extremely dense matter that collapsed within the first quintillionth of a second after the Big Bang, subsequently dispersing throughout the universe in ways that could explain the dark matter we know today. Now, physicists have discovered that this primordial process might also have produced some unexpected companions, smaller black holes with an unprecedented amount of a nuclear physics property known as color charge. These smallest, supercharged black holes could represent a completely new state of matter and might have evaporated just a second after forming. Yet, they could have influenced a significant cosmological transition, the formation of the first atomic nuclei. Physicists suggest that color-charged black holes might have affected the balance of fusing nuclei in ways that astronomers could one day detect with future measurements. Such an observation would compellingly indicate that primordial black holes are the root of all dark matter today. Even though these exotic creatures are not around today, they could have influenced cosmic history in ways that might reveal themselves today in subtle signals, says David Kaiser, the Germeshausen Professor of the History of Science and a Professor of Physics at MIT. The idea that all dark matter might originate from black holes gives us new things to search for. The black holes we know and detect today are products of stellar collapse, where the core of a massive star collapses under its own gravity, forming a region dense enough to warp spacetime and trap everything, including light. These astrophysical black holes can range in size from a few times the mass of the Sun to billions of times larger. In contrast, primordial black holes could be much smaller and are thought to have formed before stars existed. Scientists believe that, before even basic elements formed, extremely dense pockets of primordial matter might have existed, accumulating and collapsing to form microscopic black holes that could compress the mass of an asteroid into a region as small as a single atom. The gravitational pull from these tiny, invisible objects scattered throughout the universe could explain all the dark matter phenomena we cannot see today. If this were the case, what would these primordial black holes be made of? This is the question Kaiser and Alonso Monsalvi addressed in their new study. Kaiser explained, people have investigated what the distribution of black hole masses would be during the early universe formation, but never connected this to what kinds of matter fell into the black holes as they formed. MIT physicists first examined existing theories for the possible distribution of black hole masses that began forming in the early universe. Alonso Monsalvi stated, "We realized there was a direct correlation between when a primordial black hole forms and what mass it forms, and this time window is incredibly early." He and Kaiser calculated that primordial black holes must have formed within the first quintillionth of a second after the Big Bang. This flash of time could have produced typical microscopic black holes as large as an asteroid and as small as an atom. At the same time, it could have produced a small fraction of exponentially smaller black holes with the mass of a rhinoceros and much smaller than a single proton. What would these primordial black holes be made of? For this, they looked into studies examining the composition of the early universe, particularly the theory of quantum chromodynamics QCD, which studies how quarks and gluons interact. Quarks and gluons are the fundamental building blocks of protons and neutrons, the basic elements that make up the periodic table. Physicists believe that, immediately after the Big Bang, the universe was an extremely hot quark-gluon plasma, which quickly cooled and combined